computer. And hopefully I've rebooted my computer a few times and I've changed internet connections. So maybe it will be the right thing. So everybody can hear me and everybody can see me and everybody can see the slides. Okay. So let me go ahead and do administration first. We're going to do carbon-13 NMR today and on Thursday, and then we'll do a lot of problems on the following Tuesday, and then we have an activity, and then we'll start 2D NMR. And there's a bunch of different types of 2D NMR. So what I might actually do is start 2D NMR next Tuesday, and start with just proton-proton coupling, and then do het cores and then T1, T2, and multi-length experiments there. So, but we'll see, because carbon-13 is going to be fairly simple because we don't have to worry about splitting anymore, and we only have to worry about shifts and number of protons on each carbon. So, so that's administration. I should have the homework set for carbon-13 out on Thursday. It's not due until the 30th of October. It says 31st, but that's a Saturday. So it'll be due on the Friday, the 30th of October. Okay. And it's going to be a continuation of what we did before, where we're actually adding a carbon NMR to the problems we were solving with proton NMR, and then trying to figure out which carbons are which based on the different types of spectra we have. Okay. Any questions about the exam or anything else up to now? No? No. So, okay, so what I'm going to do is I'm going to share my screen, and we're going to start with the slides. Let me put you on gallery mode up here. So, and then we start there. Again, if you think I can't hear you, go ahead and write something in the chat room, because I definitely see chat all the time. So, okay, so we're going to look at carbon-13 NMR. Okay. So the first thing to know about carbon-13 NMR, and I kind of introduced this in proton NMR, the idea of anything with a non-zero magnetic moment we can actually use as a spin-active system. And those spin-active systems tend to be things with an odd number of protons or an odd number of neutrons, which gives us an ability that not all of the spins of the individual protons and neutrons can align in a field. Therefore, we have one spin out. If we have one spin out, or a half spin out of alignment with the rest, then we can see it and probe it. Now, that does not mean we're using the exact same frequency that we would use for a proton as we do use with carbon, but we have a bunch of different nuclei. So the first one I want to talk about after protons is carbon-13. Okay. But I want to show there's some really other good examples that we can use. And I'll get to those in my other nuclei systems, where we talk about fluorine-19. The great thing about fluorine-19, it's 100% of the natural abundance. Like hydrogen 1 is 99%. Well, it looks like fluorine is 100% of natural. So it's a very strong signal. It's got a very broad range, like carbon does, that we'll see. However, it's got a very good abundance. The other good one is phosphorus. Phosphorus actually has 15 protons and 16 neutrons, and it's also 100% abundance of the phosphorus-31. And this is great for organometallic callus that use phosphorus-containing ligands, because when we start looking at those phosphorus-containing ligands, we can actually watch the shift of the phosphorus as it's binding to different metals. And so we can actually look at, like, did I actually form the compound I want? Did it displace? Is it 2 metals? Is it 1 metal? We can see all that with our phosphorus NMR. Okay, so let's go back to carbon. So carbon-13 really requires a Fourier transfer experiment, because we have such a low abundance of carbon-13. Carbon-13 is only about 1.1% naturally occurring. The other thing is it's about 1,000 times weaker in signal than hydrogen. So if we just took a single spectrum, a single pulse spectrum like you can with hydrogen, and you just ping and then those waited for a signal to happen, you get this noisy little background. You would not be able to turn any of the peaks. But the great thing about the FT experiment is that you do one pulse and one pulse and one pulse, then you keep adding those. So anything that's above the baseline starts getting added together, the baselines start canceling out, and we start seeing those peaks grow in. And if you run NMRs up at Texas State, the most common run is like, I think it's 1,048, I think, scans to get a really decent signal noise ratio. So that's important for carbon-13. Again, carbon-13 also, the more you get into the sample, into your sample without changing the viscosity extensively, the better for this carbon-13 NMR. Okay. So the other thing about carbon signals is that they're spread out over a much bigger range. Our typical range for hydrogen or proton NMR is about 1 to 10 ppm, with a couple things being above that, like aldehydes and carboxylic acids. But in the carbon signal, we actually are looking from 0, and again, TMS is used as our standard in this. So the carbons in tetramethyl silane are signified as 0 in our system. So our ppm range runs from 0 ppm, but we actually can go way up into the 200s. Most carbonyls are just over 200, and we can get some things all the way up into the 250 ppm range. So we're looking at a much bigger spectrum, as well as much bigger coupling constants, where our coupling constants in our hydrogen or proton NMRs were 1 to maybe 40 hertz if it was bonding with a fluorine, if it was coupling with a fluorine, so those were really, really small. In carbon, our coupling constants start at like 150 hertz and get bigger. So that's a significant difference there. But one of the great things about those coupling constants is we actually use pulse experiments to get rid of our spin-spin coupling. So we really don't have to worry about that spin-spin coupling constants that we see in the other one. Okay, so I'm going to show you 2 NMRs, and the one you should be familiar with is the Proton Nmr. And it has, it tells us a lot about the hydrogens. But the carbon NMR is going to help us tell how many different types of carbons we have. And we'll see them in a different light. So yeah, sorry about this being very dark, but like here. But in the case of the Proton NMR, the hydrogens next to the chlorine, of course, shifted most downfield. They have the most effect with that heteroatom there. And so they're up in the 3.5 ppm range here. Then as we go down the chain, let's see if I can actually write with my yellow ink on top of this, I think. All right. As we go down the chain, so this one right here is our first one here. And then as we get further and further away, we start getting closer and closer to 0 until we get to our methylene at the end here. So if this is our A carbon, hydrogen carbon, B, C, D, and E, we can see A, B, C, D, and E right here. So C and D are, looking about the same. If you go out 3 carbons, then that's where you see a difference between a hydrogen and chlorine. So they kind of overlap each other. Okay, so this is the spectrum we're expecting to see. And if we had a really good machine, we can actually see all the different splitting possibilities in these peaks here. So this has a nice clean triplet. This has a clean triplet as well, but these are starting to get a little muddled because of the 2 different types of hydrogens contributing to our coupling constant. Okay, so this is what we're familiar with so far. Now, ideally, what we would see is all of those different carbons, and the relative shifts are going to be similar to the shifts we see for the hydrogens as far as downfield and upfield. Okay. So if we look at a carbon NMR, we see, first of all, we have a much noisier baseline. Okay, remember, carbon is only 1.5%, 1.1% naturally abundant as carbon-13, and therefore we have a much lower signal to noise ratio, and our baselines are typically this, noisier baseline here. And notice our TMS starts here at 0, and we usually run out to a little over 200 because we can see carbonyls and other functional groups show up there. And then here is our chloroform peak, and you'll notice that has a distinct 3-split pattern on it. Okay, so from our structure, we had an A, B, C, D, and E types of hydrogens. Well, we have that many types of carbons too, and they follow the same downfield trend that we saw before. So we have A, B, C, D. Oh, sorry, D, A, B, C, D, E. Yeah, that's all of them. So the one most like the methyl group is going to be closest to 0, just like before. Okay, so quick looking back here. So notice C and D kind of overlapped each other right here because they started to look the same, but they're different enough in the carbon NMR because notice we spread this out quite a bit more. Okay, so we're shifting all the way from about 11 ppm all the way up to about 45 ppm in our system, and that gives us a differentiation. Also, notice that these are all single peaks. Okay, these are single peaks on purpose because we intentionally decouple them from anything that can couple to them, such that we have a clean, intense single peak. Okay, so what can we deduce about the molecular structure from the carbon NMR? Number one, we get the number of signals, okay? Just like in hydrogen NMR, if they are magnetically equivalent carbons, you're gonna get one signal for them, which means we have to look for symmetry, okay? If they are non-magnetically equivalent carbons, meaning that looks different on both ends, we are going to see each and every one of these because the wider ppm range, okay? Our chemical shift is going to be similar to that of the hydrogens, in which we get a downfield anytime we have electronegative atoms attached, or anytime we have double bonds or pi clouds associated with. So imagine, you know, our electronegative groups like oxygen and chlorine shifted things in the hydrogen from that 1 ppm range up to 3 to 4 ppm. And our double bonds shifted that 1 ppm up to 4.5 to 5, and then in aromatic rings up to 6 and 7, right? We're going to see that same relative shift along that great thing that we'll see in the Proton Nmr. Okay, we can do integration to this to get ratios of equivalent carbons. However, it's not a very prominent technique. There might be a couple newer techniques that make it easier, but I'm going to explain that in a minute. And what we're also going to see is coupling. And if we don't run the experiment correctly, we're going to see actually carbon-carbon coupling, carbon-hydrogen coupling, and other atom couplings. So by changing the way we do experiment, and luckily the machine now just automatically does an NOE with decoupling, and boom, we don't see it at all. Okay, so I said NOE. NOE means nuclear Oberhauser enhancement, okay? And it was actually introduced in the Proton NMR at the way end, showing you that you can have equivalent hydrogens that kind of, you can see them through space, okay? It's more important in carbon NMR, because in carbon NMR, we actually want to look at that through space interaction and through bond interaction and eliminate as many of these things as possible, because of the idea that, number one, we have a very low signal strength. And therefore, if we started splitting things and spin coupling things, then that would spread the peak out even more, making it more difficult to see the peaks. So what we'll do is we'll do this transfer of spin polarization, literally taking the spin from the hydrogen and transferring it to the carbon to get this through, to get it an enhanced effect of where we can see the carbon. Okay, so let's talk about spin-spin coupling, okay? So anytime you have hydrogens on a carbon, it wants to split that carbon, okay? And this is a single bond split, okay? Which means the hydrogens on that carbon, if you had 3 hydrogens on a carbon, it wants to be a quartet, okay? If you had 2 hydrogens on there, it wants to be a triplet. If you have 1 hydrogen on there, it wants to be a doublet. And if there are no hydrogens on there, it would like to be a singlet, okay? So without our decoupling, that N+1 rule applies in a single bond, okay? So notice we don't go through the 3 bonds that we see in hydrogens, the 3 bonds splitting in hydrogen. It's actually directly attached. A single bond attachment leads to this, the hydrogen carbon spin-spin splitting. Okay. But again, most of the time we eliminate that with a pulse sequence. Okay. So is there only that spin-spin between the carbon-13 and the hydrogen? No, there's also another opportunity in the fact that if you accidentally had two carbon-13s next to each other, they would actually couple and they would have a split. But because of carbon-13 only being at 1.1% naturally occurring, the probability of having two carbon-13s in the same molecule next to each other is really, really low. It's like 1/100th of a percent. So the idea that we would see that coupling, we really almost never see it. So the couplings we do see happen to be this single bond, carbon-13 to proton spin coupling. Now, the fact that they are so close and related, we can use that as a way to enhance our carbon signal by eliminating or transferring the spin from the proton to the carbon and enhancing that carbon signal. Okay. Now, notice that because we don't have spin in carbon-13, carbon-12 and carbon-13 don't spin couple. And they don't spin couple through more than one bond. So unlike hydrogen, which we see 2 and 3 bond spin couplings, carbon only does it through one bond. Okay, and that's one sigma bond. Okay, not a pi bond. Okay, so the fact that it does exist means we have to use some kind of technique to eliminate that kind of spin coupling to enhance our signal to noise ratio, to get a really good signal. Okay. So if we do a simple thing, what we call broadband decoupling, it's also called I'll have it on another slide, I can't remember. Broadband decoupling, what this does is this takes away and suppresses all the carbon-hydrogen coupling such that each carbon goes down to a single peak, okay? And we might see a carbon-13 coupling because that's not suppressed in this particular experiment. However, it's so small, we would never see it. It's just gonna be in the noisy part of the baseline here. So we really don't see it at all. Okay. In such low percentage. Okay, so the other thing that this does is because we have decoupled that, we've taken away the splitting, our peaks are now larger and have a bigger signal noise ratio, we actually can use a fewer acquisition times to get the same signal noise ratio than we could before. When we had it coupled, we'd have to take thousands and thousands of pulses and then try to mathematically remove all of the noise. However, when we're down to single peaks, it becomes easier and easier to acquire this spectrum. Okay, so let's talk about the number of signals possible. So in general, in carbon NMR, the number of signals possible is the number of unique types of carbon, okay? Now, what this means is that in your carbon NMR, it's much easier to see symmetry. Just like when you saw certain patterns in Proton Nmr, you could see symmetry. If you only had, 2 peaks and they seem to be equivalent number of hydrogens, but you couldn't tell. In the case of carbon NMR, you can actually see just the carbons themselves. We're not worried about splitting. So if we take an analogous compound here, where we have these are the same empirical formula here, and we take a carbon NMR, on this particular one, because we have an oxygen on this side and the methyl group on this side, each and every one of these 4 carbons has a unique signal because none of them are equivalent. Okay, which means we can actually say, okay, we have a non-symmetrical molecule, and therefore we know we have to have those 4 unique signals. Okay. However, what we can see is when we have just, again, this is an isomer where all we've done is moved where the oxygen's attached. The carbon NMR gets simpler because we have now 2 equivalent ones attached to that electronegative atom and 2 equivalent ones that are attached to that first carbon. and then our spectrum goes down. Okay. So whenever we think there might be symmetry in our molecule, what we want to look for is fewer carbon NMR signals than the number of carbons in our formula. Whenever we see that, start thinking, oh, symmetrical, start thinking rings or broad or symmetrical, where you have the same branch on both sides of some functional group. Okay, so once we've actually got this, and we'll do a few examples of this showing symmetry and non-symmetry as well. Okay, so let's talk about what we normally do. So in our normal pulse sequence, what we do is we do a pre-pulse that helps decouple the hydrogens from the system, okay? So if you just starting out, you just put your sample in the NMR, and the first thing they're gonna do is you're locking and doing all your lock stuff right here, and so nothing's actually done. Your nuclei are starting to align with the magnetic field, and they're equilibrating, and they're just sitting there, right? You're doing all your lock stuff, right? And then when you first start your experiment, it does a pre-pulse, waits a period of time, a delay, and then it actually pulses at the frequency of exciting the carbon nuclei, okay? And it pulses for a certain amount of time with a certain amount of power, and then it lets loose of that pulse, and then it listens for the ping on the back end, okay? And that ping is what's then transferred with using for your transform algorithm to get to from your time regime to your ppm regime and get the spectrum you want. Now, of course, you rarely do just one pulse because it takes a lot of scans to get enough signal noise ratio in carbon. So on the back end, on the second pulse, we actually have to wait this delay time before we do our pre-pulse. And then we have to wait for this delay time for getting the spin-spin coupling from the hydrogens to help enhance the carbons. And then we do our actual pulse on carbon, which then we can get to our second Fourier transform. And then we have to do that entire thing again and again and again and again until we get as many scans as we want. Okay. Oops. Okay. Now, to do what we call composite decoupling or broadband decoupling, we have to change it a little bit using the idea that we want to transfer some of that hydrogen's pulse to the carbon to get a better and enhanced carbon signal, okay? And so what we would do with that is, this is the pulse sequence we use. We have, once we start the machine, it waits 5 seconds, okay? That's where everything's aligning with the magnetic field. And then we do our pre-pulse, and then we wait a little period of time, and then we do that pulse, right? And so when we do that, what we see is that we have the decoupling actually happens across the entire time regime of our experiment. So if we change this and we didn't do our proton decoupling, we would have that same delay at the beginning. We'd have our pre-pulse, we'd wait, and then we'd have another power pulse where we don't do the decoupling pulse, okay? And therefore, all of the nuclei, the protons and the carbons are excited in that pulse. And therefore, in that particular experiment, we'd end up with carbon-hydrogen coupling, and we'd see a lot of splitting in our system. Without doing any of this, we would actually don't have any of the NOE on here, and what we'll end up with is a very, very noisy signal. And if we did just decoupling but not this, we'd get a very tiny signal. We'd have a very low signal noise ratio, but we would definitely be decoupled, so we'd have individual peaks just barely above baseline. Okay. So what does this look like after all the FIDs are done? Okay. So if we did that first pulse sequence right here, full NOE, which is, enhancing the carbon, and then full decoupling, we're going to end up with this really nice signal noise ratio. Notice our baseline's still a little noisy, but we have very good, 100 to 1 between the spikes on the baseline and the spikes in our actual signal. Okay. If we don't enhance the signal and we don't decouple, everything just gets spread out into this. Notice we start to see a little bit here, but these are multiplets of multiplets of multiplets, and so we don't see them very strongly. Now, if we don't use that spin-spin enhancement of taking the hydrogen spin and adding it to the carbon to get that enhancement, we get signals, but our signal noise ratio is not as good. See, this is about a third of the signal we would get on this other one here. And then if we just did NOE, where we transfer the signal but we didn't decouple, notice this one has at least one hydrogen on it because it's split here, one hydrogen on it split here, two hydrogens on it split here. So these splittings right here are indicative of how many hydrogens we have on there. So there's no decoupling. So see how that's barely above baseline, and therefore not having, even enhancing the signal but not decoupling it makes it difficult to identify which protons are which. So the most common experiment you'll see is you're going to have full NOE and full decoupling, and that's the most common experiment you'll see in your carbon NMR. Okay, so
can you explain NOE once again?
This one right here?
The NOE, N-O-E?
NOE. Oh, nuclear Overhauser effect. My basic understanding of it is that it use the spin from the hydrogen, use the enhanced spin from the hydrogen, you transfer that spin to the carbon to enhance the signal. And this is it's a through bond through space interaction called nuclear Overhauser effect. Okay. Beyond that definition, I think you need to go talk to someone else, because that is my complete understanding of NOE. Okay, so, but we can use, there is actually a 2 and 3D experiment, a through space experiment, where we can turn it on and off and see through space experiments, but we're not going to do that until the 2D NMR. Okay. So the idea is that you're actually using hydrogen to help boost the signal of the carbon. Okay. So, so that is the signal and how we get a one signal per carbon of different types. Okay. Now let's look at shift. Okay. So shift is very similar to the shifts we see in Proton Nmr in the fact that electronegative atoms and pi bonds shift things downfield, okay, away from zero. And as usual, we use TMS as our proton standard as well as our carbon standard. So it's really nice that that actually turns out to be right here at 0 as well, or pretty close to it, and everything's shifted from that right here. And then the closer you are to an electronegative atom, the more downfield you get shifted. Okay. So in this case here, this OH right here shows up in Proton Nmr because it has a hydrogen on it. However, this OH itself does not show up in carbon NMR because it's not a carbon. However, we can see that the carbon it's attached to is the furthest downfield because it's adjacent to that, directly bonded to that electronegative atom. Okay. Now those general shifts, again, you don't have to memorize them. It's just knowing where to look for them because we're going to be using our tables on our exams. But the idea is that, you know, that same kind of concept works for both carbon and Proton NMR. Okay, so we have some nice trends, kind of like we had in Proton NMR. The more hydrogens you have on it, the closer you are to 0. So the methyl groups in a long alkyl chain tend to be closest to 0. When you have a CH2 group, that's shifted up. And again, these are sp3 hybridized carbons. And then if you just have one hydrogen on it, shifted a little higher up. As you add electronegative halogens, they can shift significantly. Like iodine, it's big and fluffy and polarizable, so it does not shift it as high as bromine or chlorine. Notice those shifts are much higher because those atoms are getting more electronegative and smaller. Okay, so it's a more polarized bond. So we see that. When we start attaching oxygens to carbon, it's also affected by whether or not there are hydrogens on there. But when you start attaching oxygens onto carbon, they shift it into the 40 to 80 ppm range. Okay, when we do that with proton NMR, we're shifting in the 3 to 4 range, right? So it's analogous in that. Our triple bonds are a little bit less than our double bonds. It's 50, 65 to 85. Our double bonds are signature around 100 to 150. However, the benzene ring's a little higher because of the resonance energy, and we can actually spread it out a little bit more as well, depending on what the substituents are. Electron donating substituents versus electron withdrawing substituents, or anything that polarizes it will make it a change in that. The carbonyls are always above 150, okay? And they shift around a lot based on what's attached to them. So a carbonyl that's an ester is at the lower end of 160 to 180. The amide, again, it has a lone pair on that nitrogen, so it's going to be in that 160 to 180 range. When you do the carboxylic acid, because of the enhanced resonance structure, it actually shifts it a little bit higher. And then our aldehydes and ketones tend to be the highest because they have no other electronegative atoms on there. They only have carbons or hydrogens on there, and so they're shifted higher. Okay, with the ketones tending to be the highest, just above 200. Okay, but again, don't memorize them. The general trend we saw in Proton NMR is the same. Electronegative atoms and high count move things downfield or to the higher numbers on your spectrum. That's downfield on my side, it's probably that way. Okay, so that being said, we can kind of just go and tackle a proton NMR here, okay? So just from shift here, this is our proton NMR here, and this is our carbon NMR here. And just from this, we're thinking, ooh, maybe, gosh, it's got a splitting pattern here. It's got a splitting pattern here. This looks like maybe a quartet and a triplet and a singlet. I'm sorry, triplet right here. So, we might have, this might be a CH3 group because it looks like these both have a CH3 group here. This looks like maybe a CH2, but we don't have an IR. So we can't really verify the fact that we have how the connectivity, is it in the ether? Is it something else? Okay. So what we do is we go to the carbon NMR, okay? And we see that, oh, way down here, almost to 200, this is like 190 right here, we have a peak, a carbon peak. And we have a total of 1, 2, 3, 4 carbons here. In the proton NMR, we have 1, 2, 3 carbons with hydrogens on them, okay? So that means we have an additional carbon that we didn't see in our proton NMR. And it doesn't have any hydrogens on it. But based on its shift, what is it?
Is it an aldehyde?
Well, what's the carbon? What's the carbon itself? Is it a
Carbonyl?
a what? Carbonyl. Okay, yeah, I got one in the chat as well. Carbonyl. So we have a carbonyl there, okay? Now, in our proton NMR, if we had an aldehyde, we'd have a peak way up here in the 10 or 11 range, which we're not showing here. So I think maybe it's an aldehyde. But we do have a carbonyl, and because of the shift, 190 ppm right here. And now we have something up here. This is, let's see, that's 20, 30, 40, 50, 60. This is 60 ppm. So we have a carbon here and 2 hydrogens that are next to an oxygen, probably. So this carbon's next to an oxygen as well. So I think this is our carbon number 1. Here. Let me take these numbers. So that's carbon number 1 there. And then this right here, we're going to find is this carbon here, is those 3 hydrogens. And this one is, now let me tell you why. All right, so now that we know we have a carbonyl, something bonded to a negative atom, and something not bonded to a negative atom, because of this shift here. What do you think it's bonded to? It's got a shift almost 2, it's got a singlet, it's got 3 hydrogens.
It's next to the carbonyl.
So it's a methyl group next to a carbonyl, right? So let me go ahead and just erase some of these. So this right here is, oops. This right here is telling me we have a CH3. Okay. This and this is telling me we have an O CH2CH3. This carbonyl is showing up here, so I think we have ethyl acetate. Oops, sorry. Oops. There we go. So I think our compound, based on everything we see here, is ethyl acetate, which is a carbonyl with CH3O, CH2, and CH3. Now that we have the structure, let's double check with a carbon NMR. Okay. So in the case of our carbon NMR, we have number one, a carbonyl. Carbonyl shows up way down here in 190. All right, check. Okay. We have something attached to an electronegative atom. So I think that one is that one right there. Okay. These last two are probably, this one is attached to a carbon, an sp2, sp3 hybridized carbon. This is attached to a carbonyl. So I think by shift alone, that this methyl group here, and this last methyl group at the end of the chain is there. Okay. So not only were we able to say from our proton to carbon, we have another carbon that does not have a hydrogen on it, but we can use those same relative shifts to determine, oh, this is the one next to the electronegative atom, and then this is the one next to the electron group. Notice this one shifted higher than this one, so this is analogous to that, and that, and that. Okay, we'll see that same general trend a lot of the time. All right, so let's add some new information to this to help us learn even more about this carbon NMR. Okay, so now let's do a little harder. Okay, gosh, really messy, and we can't tell what our splitting is. Okay, let's just look at our proton NMR real quick. We have what looks like a 1 proton, 2, 1. That's probably 3. Oh, that looks like 4, and this one's not integrated at all. Gosh, that's a very complex structure. Oh, we have something up here, something here, and something here. Well, that's spread out too much to be a benzene, so that's probably not a benzene. Ooh, this is probably something next to an O here. And this might be split, but we're not sure, then that might be. So our proton NMR is really confusing, right? Let's go look at our carbon. Okay, so if we pull up our carbon NMR here, we have 4 big P's right here. Okay, but we have something above, so 175 is about right here. So we definitely have, sorry, let me change color. We definitely have a carbonyl. Okay, because it's really high. That's 110, 120, 130, 140. So this is 150 right here. So that makes these vinyl groups. They're not shifted high enough to be a benzene ring, and there's not enough of them to be a benzene. So I think they're vinyl groups. Okay. This is solvent. This is probably a carbon bonded next to an oxygen. And then we have 2 other unique carbons here. So, and these are both probably CH2s or CH3s. You can't tell just yet. 2s or CH2s. Okay, so let's put it together. We have a carbonyl, we have something next to an oxygen, we have, this might, yeah, maybe that's 3. So it looks like, without any additional information, we have something that looks like this. Oh, so that's 1, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I think we have a CH3 and a CH3. How many carbons is that? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Oh, we got another one. 1, 2, 3, 4. There's 6 different ones. 2, 4, 5, 7, 8. Yeah, it's got to be something like that. This is a CH2, CH3 maybe. That could be a triplet. And that could be a multi. So, just from looking at the carbon NMR, we see we have vinyl groups. We see that we have an unusual splitting. We can't identify it just with the proton NMR because our splitting is so complex. But the carbon NMR is telling us we have things that are carbonyls. We have vinyl groups. We have something bonded to an electronegative atom. And we have something that's closer to the long. Now, wouldn't it be helpful to know which of these carbons had 1 proton, 2 protons, and 3 protons on them to help you make sure that you got your shifts right? Well, we have a technique for that. Okay. So, but before I do that, let's go ahead and talk about integration. In Proton NMR, we do integration every time because it's just so common, and the strength and the relative intensities are very easy to do. But most of the time we don't do that in carbon NMR. And the reason is because sometimes these carbons take a lot longer time to relax. For example, protons, they relax in less than 10 seconds. So what we see is that our entire pulse sequence is 10 seconds wait, pulse, 10 seconds, and done. That's 20 seconds for every pulse. And so they keep going and going and going. Some of them now, the decoupling and stronger magnets, you get them down to 5 seconds. You go pulse, pulse, pulse. Carbons take up to a minute to relax, depending on how many hydrogens they have. Okay, which means if you want to get multiple scans to get quantitative NMR, you have to pulse, wait, and pulse. Okay, so it's very difficult to do. Now, one of the other things, the fact is that because the carbons of different types actually relax at different times, this is actually really important for MRIs. So when you do the magnetic imaging magnetic resonance imaging for bodies, you actually different types of things relax, and you actually see differences in tissues. So it's actually the relaxation time is important for that. However, it's a long time to look at those in a carbon. Now, why? Okay. Now, again, for hydrogens, our relaxation time is quite quick. Okay. However, because of the idea that the more hydrogens you have on it, the faster it relaxes, that you can have 3 to 5 seconds as a decent relaxation time for CH3. However, for quaternary carbon, it can take a minute or 2 for it to fully relax, meaning you have to wait that entire time and listen to your entire spectrum before you can stop. Then you actually have to delay 5 times the longest delay before you can pulse again. Okay. Because you don't want any extraneous, signal in there because it'll show up at the wrong place on your FID. So you have to wait until everything completely relaxes and equilibrates before you pulse it again. So what does that mean? It means that if you have quaternary quaternary carbons in there, that means you have to, pulse this thing, wait 20 seconds just to listen to your sample, and then you have to wait 100 seconds before you can pulse again, which means your standard collection 1,028 scans for a carbon-13 experiment would take over 28 hours. Now, there are newer techniques that allow us to do it in shorter amount of times, but it's still not as commonly done as in proton. Although for certain experiments, for complex like natural products, it's actually worth the time to do it to make sure that you have equivalency, but most of the time we don't do it. Okay. So an example for the equivalency experiment here, we're actually just making sure that the different peaks are the same. We can actually see them in this type of quantitative system. Okay, so if we, instead of doing that, trying to do a quantitative NMR system here, what if we instead were able to find a different way to tell the difference between the different types of carbon we have, okay? And so we have what we call the inversion recovery method, okay? And in the inversion recovery method, what we do is we take into account the idea that different carbons relax at different rates, okay? So if we changed our pulse sequence to include a pulse, wait a time, and then pulse at 90 degrees to that initial pulse, what we'll see is some of the nuclei have fully relaxed and come back to their normal state, and some of them haven't fully relaxed. And if they haven't fully relaxed, they're going to end up being pulsed into a different direction. We'll see that as a different signal in the FID. Okay, so if you can imagine this, if we had, let's say we're comparing something that was, let's call this a CH3, and let's call this a CH with with 3 carbons on it right here. This is going to relax about 3 times faster than the one with just 1 hydrogen on it, okay? So if we take them both in just in the magnetic field and everything's fine, we pulsed it at 180 degrees, and then we wait. When we wait, the one that relaxes faster is going to relax back into the magnetic field before the other nuclei has relaxed completely. Okay. Then if we hit it with a 90-degree signal, we'll be able to end up tilting this partially relaxed one versus this not partially relaxed one, and we end up with a different signal in the FID. In the FID, in that case, because we pulsed it while it was in its down position, it actually gets pulsed in an opposite direction of the one that was relaxed, and therefore we have a negative signal on our FID instead of a positive signal on our FID. Okay, so is it just the right amount of, what is the right amount of time here? What do we know? Well, we have to actually measure it. So what we can do is we can actually just take that, and by changing the amount of time between our initial knock everything out of alignment, knock everything out of relaxation thing. And so half of them are, some of the signals are back up, some of them are completely back, some of them aren't completely back, relaxed in the magnetic field. We can actually measure that. So let's look at that by saying, okay, this is like, let's say it was 1 second, and then we go 1 to 10 right here. So this particular thing seems to be relaxing pretty quickly. So within about 5 seconds, we're actually starting to see a positive signal coming over here. So that by waiting just that 5 seconds, we've actually completely allowed it to relax. It's now in the magnetic field, and when we pulse at 90 degrees, we get a positive signal. Okay, so let's look at this one right here. Same thing, it seems to be coming back in about 5 seconds, and we get a positive signal. Okay, this is our solvent. Notice it never fully relaxes. It never fully comes back up. So that time regime for this particular material is much, much longer, at least twice as long as for the other signals here. Now look at these 3 signals here, okay? Those 3 signals there, 2 of them actually end up completely going back and relaxing. One of them barely relaxes in the time frame of our experiment. So that means there's a difference in the number of hydrogens on this species versus that species, because the ones with more hydrogen relax faster. And notice this last peak right here doesn't relax at all. Okay. Now, we can use this inversion recovery technique and a pulse time sequence technique to actually tell the difference between 1, 2, 3, and 0 hydrogens on carbon. Okay, and it's not the Johnny Depp experiment. It's It's the DEPT experiment, DEPE, which is called distortionless enhancement of polarized transfer. Okay, so it has nothing to do with Johnny Depp. So take that out. So in the case of a DEPT experiment, what you can do is by doing that time experiment, where that in a recovery experiment, and you do it at different pulse times and angles, you can differentiate between a CH3, a CH2, a CH, or an H. Okay, so for example, in this particular one here, we have a whole bunch of different types of ones. We have 1 hydrogen on each of these. We have 3 on that one, 2 on that one, 3 on these, and 1 on that one. So we have a bunch of that. We have 3 different types here. Okay, and it kind of might be hard to distinguish between things that are kind of lumped together closely. However, by doing this experiment, you can take away everything but just the things with 1 hydrogen on it. Because basically you're saying, okay, I'm going to pulse, but I'm not going to take any data until this time where I expect my single hydrogens to relax, and that's the data that I'm going to see. Okay, and so only these 3 peaks are things with 1 hydrogen on them. Okay, so I bet these 2 are the ones on the benzene ring, and this last one right here, I'm sorry, this one right here in the middle, and these hydrogens here are the 3 peaks we see here. Notice it's 3 peaks because of symmetry on the benzene ring. Okay, so what does this look like? Now, in our book, it looks a little different, okay, but and I'll explain what it looks like here in a minute. Okay, so the idea here is that we actually look at 3 different angles of the DEPT experiment, okay? And I'll talk about those in a minute, but what we're gonna see is we're gonna see a full spectrum, typically on the bottom here, that shows all carbons, 0 hydrogens to 3 hydrogens, right? Then we show what we most commonly do is what we call a DEPT 135 degree experiment. And in this experiment, odd numbers of hydrogens are up, even number of hydrogens are down. And so that's a CH2. If you had methane in there, it'd be down as well. But so we can tell the difference between odd and even at least. So that gives us a lot of information just from that, okay? Or we can even do another experiment where we take it another 45 degrees out of thing and only the CHs show up. So we can differentiate between, between these 2 graphs right here, we've differentiated between a CH2 and a CH3 because you compare the ups of both of these. On this graph, we've told the difference between a CH2 and the CH2 and CH3. And by looking at the difference between these 2, we can now see the Cs with no hydrogens at all. Because the Cs with no hydrogens at all don't show up in either of these graphs. So now you'll know exactly which carbons have 0 hydrogens on them, which carbons have 1 hydrogen on them, which has 2 hydrogens on them, which has 3 hydrogens on them, okay? So that's the power of the DEPT experiment, okay? So why does it work? Well, it kind of works because the different angles are associated with what the angle is when it relaxes. So you have all of your nuclei aligned in the magnetic field when you start in its relaxation period. When you pulse it, it goes 100% the other direction here, and then it slowly rotates back. Well, that time at which it rotates back has a different, cyclization to it. And so in the case of 1, it's the slowest and actually has a sine theta. Okay. 2, it's actually faster and ends up 2 sine theta times cosine theta. And then 3 is actually the fastest of them and actually is a 4 times sine theta cosine squared theta. What is that? Okay, don't worry about the equation. But what it looks like when we map that out is we see this right here showing up here. And so at any particular time in the experiment, you are going to see a positive signal, a negative signal, or no signal. Okay. Notice that the C with no hydrogen is not on here. And the C with no hydrogen on it actually would look something like this, to where we're not even in a full rise yet. So that's why we really don't see it. Okay. So let's take our, just as a period of time. So if we look at our 90 degrees right here, our 90 degree mark right here, okay, 90 degree mark right here. Notice in our 90 degree mark, both the CH3s and, I hit the corner of this with my, there. Notice at this 90 degree mark here, the CH3s are at 0 intensity. The CH2s are also at 0 intensity. So the only thing we see is the CH. That's the only thing with a positive intensity. The rest of these are right here at 0. Okay. At 135, right here, the hydrogens with 1 and the hydrogens with 3 are positive. The one with 2 is negative. That's our second one. That's where we get the odds up and even down. Okay. At 180, that's where they're all wiped out completely. In fact, if you did that 180, you might see the carbon with no hydrogens on it come up. Okay, so that's why we take that pulse at different degrees, because it shows you which things have a positive signal, no signal, or a negative signal. And that's how it differentiates it on the depth experiment. Okay, all right. So let's look at that again. 135, because 135, actually has all 3 of the waveforms have a signal. 2 of them are positive and 1 of them is negative. We can see that in the 135, our 1 and 3 are positive and therefore up. Our 2 was negative and therefore down. And so these are the ones with 2 hydrogens on. All of these are the ones with at least 1 or 3 hydrogens. Now, if we do that 90 degree again, those 2 hydrogens go away. Notice at a 90 degree, the 2 hydrogen and the 3 hydrogen go away, and we're left with just the 1 right here, which means at the 90 degree, these are all the peaks with 1 proton on it. Okay. And then if we go to our last peak here, right here, at our 45 degree, we see all the protons, but no quaternaries. Okay. So that's at 45 degrees, which is, if we looked on the spectrum here, it would be right here. Notice there's a peak on all of them. And again, that quaternary is going to be barely above baseline because it's going to be a very long wave function at this point. And so we only see all of them, but the carbon with 0 hydrogens on. And then if we looked at our normal spectrum, now by comparing and contrasting all 3 of these, you should be able to pick out 1, 2, 3, and 0 hydrogens on each of your carbons. Okay, so let's try it. Okay, so let's first blow up our proton right here. Okay, let's see, looks, I don't know, kind of suspicious. I think it might be benzene because it's right up there in the benzene range, right there. And I think that is probably solvent, maybe water and acetone, but I'm really not sure. That's not really a lot to go on. I can't see any splitting here. The protons doesn't tell me a lot. Okay, so let's look at the carbon NMR. So the carbon NMR tells us a different story here. The carbon NMR tells us we have more than we think we have, and they're not what we thought we had. Okay, so we have 1 here, but that might be solvent, that might be acetone. We should probably look in our book. Hey, we have a table in our book that shows us where solvents show up in both proton and carbon NMR. So in our carbon NMR table, I think it's in carbon here. Yeah. All right, it's Appendix B. It's chemical shifts of laboratory solvents and impurities. And I think this is acetone. So we're going to look for that. CH3 in acetone is right at 30 ppm. And let's see, there's also going to be a peak at 207 ppm. But we'll see. So there might be acetone in our system. But we'll see. All right. So anyway, so that's Appendix D. In my book, it's 241. It's probably 245 in the newer edition. C0 granule bar. Okay, so let's take a look at what we see. We have something above 200, so that's probably a carbonyl. We have something at about 100, and then, oh, we have something way shifted. We have something also there. Okay. So in our first spectrum, we have our 0 degree, which should have all of our carbons. Okay. And then at 45, 90, and 130, we should have a differentiation between 1, 2, and 3. So at 90 degrees, what should we see? So at our 90 degrees, we're only going to see CHs. Okay. And at our 45 degrees, we're going to see all but quaternaries. And our 135, we're going to have ups and downs, right? So let's look at our 135 again. Our 135 again, we have 0 downs. Okay, that means we have nothing with 2 hydrogens on a carbon. Okay. And it looks like we only have 1 carbon with any hydrogens on it at all. Okay. So we have 2 types of carbons and only one of them has hydrogens on. So where are we at? So we have, let's see. So I think that's an impurity. So I think 1, 2, 3. We have, I don't know, they're all up, so it has to be a CH or a CH3. But wait, the 45 says it's a CH. So we have a CH right here. We have some kind of carbonyl compound, and we have some other carbon in our system. And it's way shifted up.
With carbonyl in it.
Is it a carbonyl what?
In benzene ring.
Okay, so a benzene ring. Those would all have a single hydrogen on them, wouldn't they? So if we had
There is one carbonyl.
with a carbonyl, so this would be our quaternary carbon. This would be our equivalent hydrogens in the benzene ring.
No, I'm saying that carbonyl within the benzene ring. The carbonyl group within the benzene ring.
Then it wouldn't be aromatic. Like that?
Okay.
Yeah.
Yes.
With the double bond.
Yeah. Yeah.
I like the idea of having a benzene ring, because notice those are all having 1 hydrogen on them. And a carbonyl, and it doesn't show us what's above here, so maybe an OH. So now we have a lot more information given by our carbon NMR, especially when we add our depth experiment to it. Okay, so let's try another one. Okay, so if we look at our proton NMR right here, right away it looks like, well, maybe a benzene ring again. Something next to an oxygen and like this. And so this looks like a 2, 3, maybe a 2, 2, maybe a 2, 3, 3 here. And this looks like a splitting Oh, this is a 2,3, sorry. This looks like an ethyl group of some kind right here. Probably bonded to an oxygen. Well, no, it's kind of low for an oxygen. All right, so that's about all we can tell there. Let's look at just the carbon NMR. Okay, so carbon NMR says we have more than one type of aromatic ring. And we have two kind of aliphatics. I think this is our solvent here. Where does chloroform show up in the carbon NMR?
77.
77, and it's a multiplet because the chlorine, okay? So let's see, that's 10, that's 9, that's 8, that's 7, so it's probably chloroform at 77 there. We probably have some kind of carbonyl here. And we have two peaks here that are probably that ethyl bridge here. So it looks like we have a benzene, a carbonyl, and an ethyl bridge here, okay? Let's see which of these carbons have one hydrogen on them, 0 hydrogens on them, and 2 or 3 hydrogens on them, because that'll help us differentiate these and tell us if we have one or more substituted carbons on the benzene ring. Because the ones with hydrogens will show up, right, on the depth experiment. The ones without, with the substitutions on them, will actually go away on some of the depth experiments. So let's take a look at the depth experiment. Okay.
For real quick, for the benzene carbons on the carbon NMR, one of those lines looks a little bit thicker. Is that meaningful?
It might be 2 lines. It could be that we have a total of 3 different kinds of benzene carbons here. But we might be able to tell that when we look at the depth experiment. So without the possibility of blowing up, it could be a doublet. It could be 2 different kinds of carbons. So, but let's see with the information we're given. All right, so if we look at our 0 experiment, that's going to show all of our things. So it's all of our carbons. Remember, our 45 shows us carbons that have hydrogens on them, but not quaternary carbons, okay? So what that did for us is it actually removed our chloroform peak here. It actually removes chloroform too. So so our 45 experiment got rid of our 1 peak here and 1 peak here, okay? And maybe there's a 3rd peak in here somewhere because look, this changed a little bit. Okay. So this is probably a carbonyl peak because it has no hydrogen on it. This was definitely our chloroform peak, and these both have hydrogens on them, and these all have hydrogens on them. But it looks like we might have gotten rid of 1 peak in here somewhere. Maybe that's 3 peaks, and one of them disappeared during that. Okay, because this would be everything but quaternaries and chloroform. So what's 90 degree? 90 degree is things with 1 proton, right? And it looks like we have things that are 90 degrees have 1 proton, and then these have gone down tremendously. So those probably don't have 1 proton, okay? And when we go to our 135 experiment, right? We have 1 and 3s are up. 1 and 3 are up, and 2 is down. We get differentiation down here. So this is the one with the 2 on it. This is the one with the 3 on it. So this is definitely our fragment of CH2, CH3, right here. This is definitely qualified as a quaternary carbon or a chloroform in this case. And it looks like we have 1, 2, 3, maybe 4 types, maybe more. Looks like we lost maybe 1 carbon out of here. Maybe the rest of them have hydrogen on them, and we have a carbonyl. So with this information here, I think we have a benzene ring, monosubstituted, carbonyl, O, CH2, CH3. Okay, but let's make sure everything agrees. Okay, so we have, you know, a total of 5, 6, we have all of these, which I think are, we can lump those together. So that'd be one type of, 2 types of carbon, 3 and 4. So we have 1, 2, 3, and 4 types of carbon. Okay, we're consistent still. We should have one, okay, we should have one type of hydrogen here, one type of hydrogen here, and one type of hydrogen here. Let's look here. We look at our proton NMR. We have what could be 5 hydrogens here, 2 hydrogens here, and 3 hydrogens here. So that's consistent. And on our depth experiment, we have at least all of them have 1 hydrogen on them except for a carbonyl and 1 CH3, because that's our, I'm sorry, this is CH3. We have at least 1 CH2 on our system. Do you think you have an ethyl bridge attached to the oxygen? I think number one, we have the shift of that carbon and this carbon. Oh, actually, it might not be an ester. You're right. An ester would be more at 3.5. It probably is directly attached then, like a ketone. Good call. But yeah, you're right. It's not shift up enough to be an ester. It's probably a ketone directly attached. And again, the oxygen does not show up in the proton NMR because it doesn't have a proton. The oxygen does not show up on the carbon NMR because it doesn't split carbon. So we would have to go to our mass spec and our, but I think the shift alone is telling us it's probably close to the aromatic ketone. That would be probably up there at 3.5. So is 160. Okay, and it's way above that. So Ron says that the ester carbonyl was 160 to 180, and we're actually 190. So I think you're right. I think it is the ketone based on the shift of the carbonyl and the shift in the proton NMR. See? Jump to a conclusion, but we had to prove that we had the ketone.
Can you please explain the aromatic ones?
Okay. In the case of the why they're not, why it's not just one peak. So we can't really blow this up, but it was mentioned that this peak looks pretty wide right here. And so that could be several peaks that are similar on top of each other. Okay. And when we did the depth experiment where we removed quaternary carbons, it actually looks like we lost something. Notice that this looks like it might have had another peak here and that we've lost it in this one right here. So, but it looks like, we have at least 1, 2, or 3 that are all the same. It looks like we had something else though. See how this is different than that? That would account for having all of these have at least 1 hydrogen on it. We have something that may have been there that does not have a hydrogen on it. That accounts for our benzene that is attached to the carbonyl, our substitution on our benzene, because it has no hydrogens on it. Does that answer your question? Okay, good. So again, it's giving you additional evidence. You can't just jump, okay? Sometimes benzenes will show up as a single, especially if it's just like an alkyl chain or a methyl group. Because there's so little difference in the polarization there, it might just look like a single peak. But when you do the depth, you'll see that the signal chain might change because of the substitution. Okay. So with all evidence, I believe that we are correct in the fact that we have this ketone. Okay. What time is it? Okay, still have time. Great. Because I have one more problem. Okay, and I gave the empirical formula because it's hard. Okay. So what we're going to do is we're going to look at proton first, and then we're going to look at the carbon, then we're going to look at the depth. Okay. How do you not account for small peaks? Most of the time in carbon peaks, anything that's in the baseline, you might not. Oh, like the 90 degree. Oh, when you're looking at the depth, see how these are. So the question is, why did I kind of not pay attention to these peaks in the depth? And the point is that as we go through the different degrees, notice how these are approximately the same intensity as they were in the carbon nanometer. They've minimized here and then they've inverted here, okay? So when we're looking at that, notice these peaks have almost the same relative intensity, okay? So, and it goes back to where you are in your cycle here. So what you can do is you can be just slightly, like everything has a slightly different relaxation time. And so if you're just slightly on this part of the spectrum, you'll see a little teeny positive peak, but really it should have gone to zero, you know, plus or minus a couple seconds. And so we're just seeing a little bit of that residual peak, okay? But the fact that it has definitely decreased, it has definitely changed from the 45 degree experiment, which only shows CHs, to the 90 degree experiment, which only shows things with hydrogens on them. The 90 degree only shows things with one hydrogen on. And so notice these didn't change very much. So these are probably just somewhere on that little hump. But when we do our 130 experiment, we definitely have the ups and downs. Okay, did that answer your question? Yeah, okay. All right, now let's do the hard one. Okay, so the first thing we want to look at proton. Boy, probably a benzene ring. Some big thing that has a lot of hydrogens. There's a hydrogen over here, maybe an alcohol of some sort over here. Gosh, 1 to 1 to 1 to 1. Oh gosh, well, we can't have two benzenes, so we probably just have one benzene ring based on the structure here. It's gonna have a weird splitting pattern on that, but let's see how many carbons we have. Okay, so right here, let's go down, let's look at this end. So there's no aliphatic hydrogens right here. This is chloroform, well, 1, 2, 3, 4. This is a big triplet at 40. So what solvent do we have here? Let's see, acetone's at 30. That's at 40.
Is it DMSO?
Let's see, what's DMSO show up at? DMSO shows up at 40. Perfect. So we're in DMSO. Okay, so this is our solvent peak for DMSO, which might account for our, well, usually in DMSO, we see a nice sharp peak for exchanging hydrogens. That's interesting. And this is also our DMSO. Oh, okay. So that's something to look at. So we have no aliphatics, so let's look at what we have. So it looks like we probably have aromatic in this range, but this is a little high for aromatic because remember, aromatic goes up to about 80, 180 or 185. And this is all the way down to, oh gosh, 110. So this is definitely our C double bond C areas. And we probably have a carbonyl here or something like a carbonyl. Okay. We have 1, 2, 3, 4, 5, 6 different peaks here. Benzene plus a carbonyl. Our empirical formula is 7 carbons and at least 1 oxygen. So at least one of those oxygens is used up in that. So 7 oxygens and a carbonyl. That's interesting. Ooh, big old peak here. Interesting. All right, so let's go look at the depth right here. So at our 0, that's all of them. Let's see. And at our 45, that's everything but quaternaries, right? So our quaternaries are gone. So that accounts for our carbonyl. So this is a quaternary carbon, and this is a quaternary carbon. Okay. So these are carbons with CH2s with at least one hydrogen on them, and only one hydrogen on them. And notice that this is our 135, where our CH2s, our one hydrogen and three hydrogens are up, and our two hydrogens are down. We have no down peaks at all. So these are probably the benzenes. Okay, and we have a di-substituted benzene. And we have some kind of carbon way up here at a carbonyl. So let's figure out what we have. Based on that information, we have a benzene. And based on the fact that we have 4 protons and 4 different carbons with hydrogens on them, and none of them are equivalent, I'm thinking we don't have a symmetrically substituted benzene. We have an ortho substituted benzene. Because when you have an ortho substituted benzene with an X and a Y group here, you're going to end up having 2 quaternary carbons, and then A, B, C, and D are all going to be different. So we have a total of 6 different carbons because let's say this is an electron withdrawing group, and this is an electron donating group. That's going to shift everything everywhere. Okay, so I think we have an ortho substituted benzene ring based on this pattern. And we probably have a carbonyl of some sort. Now, that carbonyl is right at 190. Where do the carbonyls show up in maybe a carboxylic acid or an amide? Are they shifted higher or lower? We have a table for that. So in our system here, we have, let's see, amides, aromatics, we have lysyl tables. So let's see, carbonyl that's attached directly to a benzene is around 197. An aldehyde attached to a benzene is 192. Aldehydes and ketones, carboxylic acids are 185 to 150 to 185. So, and that carbonyl does not have a hydrogen attached to it, so it can't be an aldehyde. So it's probably a carbonyl. So let's see what we got. What do we have left? Okay, we have 6 of our carbons, so we have a carbonyl, and then we have an NO2. Right, is that all? No, because we, 1, 2, 3, we have 4 hydrogens used, so we have 3 hydrogens. Oh, I know what we have. We have these hydrogens. These look like hydrogens that exchange. These look like hydrogens that exchange. This looks about half that. So maybe that's 2 hydrogens here, and that's 1 hydrogen here. And they're exchanging, so the integration's not exactly right. Ooh. So that gives us a carbonyl, a nitrogen with 2 hydrogens on it, and an OH. Let me redraw that, sorry. It's too far to the side. Where would an amide, OH, I mean, NH2 and OH. 1, 2, 3, 7 carbons. 1, 2, 3, 4, 5, 6, 7 hydrogens, 1 nitrogen and 2 oxygens. where would that amide carbonyl show up? So an amide carbonyl, it would go maybe 195, but we'll look at table 420. 420, an amide carbonyl should be shifted 169. Oh, we do have a 169 that disappeared when we had a quaternary carbon here at 169 that shifted away as well. So let's see, does everything else fit? Proton fits. We have an electron donating group and electron drawing group, meaning that protons A, B, C, and D would all be different. They all exchange.
I'm a little confused about the amide in the Proton Nmr.
Yeah.
The amide in Proton Nmr, isn't it appear lower than the around 4-5?
So you pick an amine and a carboxylic acid?
Yes.
Okay, let's look at the proton NMR then. Where would an amide proton show? We have a table for that. We got supporting information. Okay, okay, it's not in a table. I have to look at the actual chapter. Proton bond, nitrogen. They exchange. Aliphatic. Protons on nitrogen atom and amine salts can exchange at a moderately as high as 8.5. The monosubstitute is going to show up around 4.5. Well, I think, well, first of all, we're out of time, but I think that might be a consistent one for what we see. It matches the depth experiment, it matches the carbon, it matches most of the hydrogen proton spectrum. I'll have to double check my notes. I actually didn't look up what it was. I want to figure these out as we go. But, so I'll double check to make sure that's what it is, and then I'll just double check to make sure that's what it is. And if it's something else, we'll talk about it on Thursday. Okay? So I'm going to go ahead and stop recording.